Okay, let's begin. So, in all these classes, we have been looking at how to implement op amp, and op amp essentially was a high gain amplifier. And if you actually think about it, we have been looking at two variants of this amplifier. One was taking in a single input, amplified it, and provided a single ended output. And this was basically your common source amplifier, and you can increase its gain by putting cascodes, folded cascodes, and all stuff. And we also looked at the case where the amplifier takes two inputs and amplifies the difference and gives a single ended output, right? And this was our 5 transistor diff amp, and again you can do all sorts of techniques to boost its output impedance. Okay, now all both these, and we also saw how to combine multiple stages to get higher gains, and we also saw techniques to make sure that the multi-stage op amp is stable in negative feedback, and we saw Miller compensation and feed forward as two techniques that help us stabilize the loop. Now these op amps are nice and useful, but in practice they have some issues, especially when you implement it on chip. And one of the reasons is the following. Say you make a big system on chip. So basically say it has multiple blocks like this, and note that these blocks need not just be op amps. These could be some other blocks implemented using op amp. But the point to notice, all of them will have a single ended output like this, because all our op amps have been giving a single ended output, right? Now let's say you have some system like this made with multiple blocks, and as you all know, everything must be powered by a VDD. And all of them will be connected to the ground. Now this is all nice and good. If this is VDD, everything is powered by VDD, but this is far from reality, because this line here, this essentially is a metal line that is connecting these 2 points, right? Now this is not an exact short, right? So in practice, what do you think this has? It will have a resistance and it will have an inductance also, right? It's just a metal line. It will have a series resistance and an inductance. So the real scenario is this. So we have a resistor and an inductor in each of these lines. Okay. The same will happen in the ground line also. Let me quickly draw that. Okay. So now you see that the first stage, let us say it's providing an output, and the output is available with respect to this ground. Say that some VG1, right? Now it is obvious that the ground that is available for the second stage is not the same as the ground that the first stage was using, right? Because there is going to be some current flow in this path, and that is going to change this voltage. Is that right? And this current obviously will be dependent on the current consumed by all the other blocks, right? It is the current returning back to the ground, and this will have components of the current consumed by all the other blocks, like all these currents, a fraction of them will be returning back, isn't it? So this potential, the point is the ground here that the second block sees is not the same as the ground the first block was referenced to. So although this output here is available like this, by the time the second block sees it, it is going to process some other voltage, and the situation is going to get worse as you go further down the chain. Okay, so the basic problem is the fact that the output which we have defined as the voltage between 2 points, is right now available such that one voltage is the output of the system, and we are defining its voltage with respect to a common ground, right? Remember, voltage is always difference between two potentials. Here one of them is our output and the other is a common ground. So this seems to be a problem because output is defined with respect to a common ground. Okay. Now the same will happen on the VDD side also. So let me quickly show that. And here for simplicity, let's assume that the ground is fine and the major issue is at the VDD to illustrate the point. Let me erase all these guys. Okay. And let's say for example, let us say this first block contains only switching circuits. So basically this circuit will operate on a periodic clock like this. So if you have such a switching circuit that operates on a periodic clock, when do you think it will consume power? Yeah, I mean basically if you're not familiar, you can think of switching circuits as some digital gates, right? Digital gates are essentially switches. So let's say these are CMOS logic gates. What is the static power consumption in a CMOS logic gate? 0. So when does it consume power? During the clock transitions. Okay. So every clock edge you will be drawing spiky currents like this, right? So the current drawn here is basically some spiky current. So that current has to come here. So now this voltage now is proper VDD, but the supply that reaches here, let's say it's VDD1, that is obviously not the same as the VDD we want. It is VDD minus the drop across this entire branch. It is essentially the drop across the resistor, which could be small, but the main issue is the drop across the inductor, right? Because what is the voltage across an inductor in terms of its current? Is derivative of the current. So this is a spiky current. Derivative of it is going to be huge. Okay. So the voltage here is going to see huge jumps, and the same will propagate to the later stages also. Okay, so because of the presence of this inductor here, the supply voltage will see huge jumps. Right? And it could easily happen that these jumps are so high that the transistor connected to these points can go out of saturation. Right? So this is a serious problem. So what do you think we can do to reduce its effect to some extent? Okay, let's think. See, the main issue is that we have the spiky currents flowing here, right? Remember, the issue is not about the spiky current. This block will have to take spiky current. That is the behavior of the block. That is something we cannot change. So the issue is not the fact that we are drawing spiky currents. What is the real problem? The currents are flowing through this inductive path. Okay. So what is the solution that you can think of? No, like in words, right? The issue is the fact that there will be spiky currents. And the problem now is these currents seem to be flowing through this path. So what could be a solution in words?
It should not pass.
It should not pass through that path. So you should provide some other path for those spiky currents to flow. Right? Makes sense? And I mean, if you think about it, these currents are essentially very high frequency currents. Right? So you should provide a low impedance path for this current so that the currents will prefer that path. A lower impedance compared to this branch. Right? So you should put something such that it offers a low impedance for these high frequencies. But at DC you don't want anything here, right? Because you want the DC VDD to appear directly. So at DC, how do you want this block to behave? Huh?
Open.
It should be an open. See, for high frequencies it should be a short so that all the currents will flow. At low frequencies it should be open. So what is a block?
Capacitor.
It's a capacitor, right? So one solution is we can actually go and put a capacitor like this. Make some space. Okay. And this is often called the supply bypass cap. I mean, this shouldn't be very surprising, right? Because you know that if you have an infinitely large capacitor charged to some voltage, how does it behave like? It's a voltage source. So if you have a very large capacitor charged to some voltage and put here, it behaves like a voltage source. So it's as though you put a local voltage source here, and the voltage source is providing all these currents, right? So now it is clear that the capacitor will provide all the spiky currents, and the fraction of the current that will flow here will be very small. Okay. I mean, you can also think of it by looking at the impedance. So probably let me draw that separately. So this is the VDD and this is our inductance path, and here is where we have connected our block, right? Now if I look at the impedance here, how do you think it will look like across frequencies? At low frequencies, at DC, what is the impedance? It is going to be the resistance. So let's say the resistance is small, so it will do something. And as frequency increases, it will keep increasing because of the inductor. So you'll have something like this, right? Now you know that if this were a complete short across all frequencies, you don't have any issues, right? So now we have a low impedance for low frequencies, but since at high frequencies the inductance offers a very large impedance, we have a large drop, and that is what is causing issues. Okay, so now the act of putting a capacitor, let's see what it does. Now let us say I go and put a capacitor like this. The capacitor impedance is something like this. Okay. So now the effective Z out is the parallel combination of this and this, right? So at low frequencies we have parallel combination of this large resistance and this small resistance. It will be dominated by the smaller one. So you'll have something like this. And at very high frequencies, what will dominate? Smaller one. The capacitor is going to dominate like this. So in between you will have probably something like this. Just a rough sketch, right? So now we can clearly see, right? Earlier the impedance was actually increasing as you kept increasing frequency. Now the moment you added the capacitor, overall you see that the impedance is actually relatively small across the entire range of frequencies. And in fact, if you put a very large capacitor, say infinitely large capacitor, the capacitor will do something like this, right? So if you take the parallel combination, it's going to be this short. So of course, if you want to completely eliminate the issue, you need to have an infinitely large capacitor. In practice, you cannot have such a large capacitor, and you can't have a very large capacitor also, because this capacitor will have to be on chip, because remember, this capacitor has to be right at the supply of this block, right? If you keep it somewhere here, there is no point. You should keep it as close to the supply of the particular block as possible, right? So you'll have to have it on chip, and you can't have a very large capacitor, so you can put only some capacitance. So the problem will get reduced to some extent, but you can't eliminate this VGD jumps completely. Okay, so even after doing all this, your actual VDD 1 will be the required VDD plus say some I'll say VDD noise of T. That's okay. I mean, it's just some random variations will be there on top of the actual VDD we want. So now let us see what will happen if you have such changes in your supply voltage. And for that, let's take our 5 transistor OTA. So let's say this is some I0, and NMOS transistor I'll call MN, PMOS transistor say it's MP. We have the diode connection, and right. Now what we have is, on the supply we have a small variation, right? And if the variation is small enough, I can use small signal and estimate what fraction of it comes to the output, isn't it? So let's try to find out what happens. So how do you propose we go about solving this? I mean, what are we supposed to find? No, what is the thought process? I mean, the idea is, see, we know that there is going to be some variations in the supply. I am interested in finding what will happen to my output, because I am finally interested in my small signal output. Okay, so basically I want to find the transfer function from here to here. That's all. Small signal gain. So how can we find? Huh? Sorry? Yeah, we can find the short circuit GM and the output resistance, right? So we don't have any other inputs. In small signal, the current source is open. So we can try to find the small signal GM and R out. I mean, you can also draw the entire equivalent incremental circuit and solve it. But finding short circuit GM and R out is easier, because for finding the short circuit GM, you'll be shorting this guy. So that is going to simplify the circuit to some extent. Your calculations will also become easy. And R out, you already know the R out for some basic blocks. So you should be able to find it quickly. That's all, right? And here, what is the R out? What is the output resistance here? Parallel combination of the NMOS and PMOS, right? So let's find the short circuit GM, and for that I am shorting the output. I am interested in finding the short circuit current here, right? So I'll probably replace this guy with its incremental equivalent to get some clarity. So here I'll have okay. So this current source is GM-VGS, and this is say R0 of the PMOS. So the short circuit current will have contributions from this current, right? Maybe I'll use a different color. Let's say this current, and the current that comes here, right? So what is the current flowing through the R0 of the transistor? What is this current?
VDD by R0.
Right? So I'll use the same color maybe. So it's Vn dt by R naught of the PMOS plus, let's say I call this current as I1. So this current will have to flow like this, right? So if that is the case, what can you say about this gate voltage Vg? What is the current in this direction? No, what is the, I mean, I have already marked some currents, right? In terms of the marked currents, what is the current flowing up in the left branch? Minus I1. So what is the gate voltage then?
minus I1, मतलब R not that. Okay.
No, the current flowing here is minus I1.
Minus I1.
Minus I1 will flow through the impedance here to generate the gate voltage, and what is the impedance there? 1 by Gm, right? So it's minus I1 by Gm of the PMOS plus I'll have Vn dd, right? Because I mean this is not ground, right? This is raised to Vn dd, so this is okay. Oops, yeah. Let me. This is Vg, right? So what is the gate to source voltage then for the PMOS transistors? Minus I1 by GMP, right? Because this is the gate, this is the source. So then what is the current here? This current is GMVGS. So what is that current?
Minus
GMP VGS is what? Minus I1. Okay. So the current flowing up, this current is minus I1. So this current is plus I1. So what is the total short circuit current now? So this plus 2I1. Okay. Fine, right? So now let's find the current I1, and current I1 is essentially the current flowing in this branch. So I'll redraw that branch for clarity. So we have something. We have the NMOS. Oops, not ground. And what is the impedance connected to the source of NMOS? What is the impedance here? 1 by Gm of the NMOS, because the drain is ground. Okay. So here I'll have Gmn, and let me complete the circuit. So here I'll have my Vn dt. Okay. So I mean, to find the current flowing here, I just need to find the impedance looking here, right? So Vn dt by the impedance, let's say Rx, is the current I1, right? So what is the impedance looking down here? 2R0. We have already done this, the cascode. So I'll probably replace it by a single resistor 2R0. Okay. So now what is the total resistance Rx? Rx is the impedance looking here, mind you. This is Rx. What do you think this is? Okay, see. I have this direct connection here, right, from gate to drain. So this basically is a 2-terminal element or a 3-terminal element now? It's a 2-terminal element. So it's going to be a series combination of those two resistances, that's all. I mean, if the gate connection was not there, I mean this connection was not there, I cannot use the series combination things because it's a 3-terminal device. Now that I have this, I can find the impedance as series combination of this impedance and this impedance. So what is this impedance? It's 1 by Gm. We can work it out. So it's going to be 1 by Gm of the PMOS plus 2 R0n. This is as good as 2 R0n. Okay. So then can you help me find out the short circuit current? What is this? Plus what? to R naught n. Okay.
Hmm.
So the current I1 here is essentially, let me probably write that also so that there is no confusion. The current I1 is basically V in dd by Rx. Okay. So what is the short circuit GM then?
Parallel.
It's not one, it's 1 by R naught n parallel R naught B, right? I mean, be careful with the dimensions. So this is my short circuit GM. You also know the output resistance. So what is the out by? It's 1. Okay. So my R out is this, GM is this. So what this says is that if there is any change in my supply, that is going to get directly reflected at the output. So do you think this is good or bad? This is bad. I mean, simply because I want my system to respond only to the input I provide here. Whatever I am applying to the gate is the input to which I want my system to respond. But now looks like I am also getting some response due to any variations in the supply also. Okay. So this is bad, and there is a term to quantify this, and that is called power supply rejection ratio, or PSRR. And definition is straightforward. It is basically the gain, the actual gain you want, that is the gain from your desired input, which is from the gates to the output. What is the gain from there? GM of the NMOS times the R naught. So GM of the N, oops. This is the actual gain you want from the inputs, which is the gates to the output, divided by the gain you have from the supply to the output, which is 1 in our case. Okay. So this is the PSRR in our case, and ideally what do you want this PSRR to be? You want ideally PSRR to be infinite, right? Okay. But here you see that we are not doing so great with respect to PSRR. So the bottom line of all these discussions is that if you have a single-ended output like this in our systems, it is highly sensitive to any variations in ground as well as variations in VDD. Okay. So in short, I'll just write it like this. If you have single-ended outputs, it is highly sensitive to any, I will say, common mode disturbance because VDD and ground are all common signals to all blocks. So any variations that happens in these common lines, that will directly affect our output. Okay. And there is one other problem with single-ended outputs. Let me quickly explain that. So let's say this is the output signal and you want to connect it to the input of some other block. You will basically have a metal line like this and connect it, right? Now let us say there is some other signal that is routed like this on a different metal. So I mean these are at different heights. Okay, so this is our actual signal. On top there is some other signal that is getting routed like this. Okay. So let's say I call this signal some V2 of t. This is our signal VO of t. Okay. Now from each of these metal lines to ground there is going to be some parasitic capacitance. Now on top of it, whenever I have two metals overlapping like this, wherever they are having this overlap, there is going to be some small capacitance. So to model that, we can model it like this. So this is our C1, where we should have had only V of t. This is say V2 of t, this C2, and in between there is going to be some overlap capacitance like this. Fine. So now any variations in this signal V2, that is going to get coupled to our output. And what is the factor? What is the fraction of V2 that will couple to the output? Yeah, it's going to be the capacitive division, COV by COV plus C1 times V2 of t. Okay. So again your output is getting disturbed if there is some other interfering signal passing nearby. Okay. And not just that, this our output signal, that will also change the signal V2, right? So we'll have a fraction of some alpha times V of t also getting added. Right? I mean, it is not like only your neighbor shouldn't come and put his garbage in your home. You should also not put your garbage in his home. It should be mutual, right? But here you see that if you have single-ended signals, you are going to have severe interference, right? So again, this is sensitive to interference. Okay. So the solution to all these problems is straightforward. So if you think about it, the initial problems we have is because our output signal is defined as a potential difference between one line which is local to our block and one other line which is common to all the blocks. Because that second line is common to all the blocks, everyone is coming and dumping their garbage and disturbing it. So if you want to be immune to those disturbances, what do you think we can do? I mean, the reason is this, right? The output is defined as the potential difference between two lines. There is no issues with this line because that line is local to my block. The issue is with the second line, and that second line being common to all the blocks, I am having issues. So if I don't want to have any issues, what can I do to the second line? I should have a separate second line. Like just like how I have a local single-ended output, now I can have two lines locally and say my output is defined with respect to those two lines, right? So that's the idea. So now instead of having one line locally, you have two lines and you say your signal is the difference between these two. That's all. Okay. So this I will call VO positive or VO plus and VO minus of t. Okay. And this is called the differential signaling. Okay. So let's quickly see if this is going to help us in all these problems. So I can copy this to illustrate the point. Cool. So now the scenario is same, but the only difference is I am going to have two output lines, right? Something like this. Okay. This is not shorter to the supply. Okay. So now we'll have the same scenario. The ground is going to get disturbed. So Vg1 will be different from Vg2, right? But if you think about it, as long as we are interested only in the potential difference between these two voltages, even if this guy changes, both of them individually will change by the same amount. So if you take the difference, we are all set, right? Is that fine? Okay. So as you see now, this is going to be immune to variations in ground. So let's look at the issue of interference before coming back to the supply rejection. So now again let's look at the case of let's look at a case where we have an interfering signal nearby. So now we'll have two lines like this. So there will be two parallel lines like this. These are our two output signals. And let's say we have some other interfering signal passing at a higher or lower metal layer. So let's say this is my V2 of t. So let's say this is VOP and VOM. So let's model it as a lumped element. So I have VOP. From here to ground I'll have some capacitance. VOM, from here to ground I'll have some capacitance. Same is the case with V2 of t. And whenever I have, now I have two metal lines like this, one more line is crossing like this. So I'll have overlap capacitance for each of them. And what can you say about the capacitance values for these two? Can you comment on the values of the relative values of these capacitors?
These both.
Overlap capacitors.
With respect to?
No. The question is, two lines are there. Some third line is crossing over them. I want to find the overlap capacitance of these two. How do you think they'll be related? Same. Okay. So as long as these two lines are very identical, which is what we have to ensure, the overlap capacitance is going to be identical. Okay. So now we'll have the same scenario. Along with VOP, we'll have some factor, let's say beta times V2 of t. Here again I'll have some beta times V2 of t. If I take the difference, again I seem to be having no issues. Okay. So let's look at what will happen to the interference that we are causing to V2. Now again, due to VOP, I'll have some, say, gamma times VOP of t here. Now we'll have the same factor gamma for the other output VOM. Now if I want this to be equal to V2 of t, that is, I don't want V2 to get disturbed. So if this is the case, what can we say about VOP and VOM? They should be negative of each other, right? So basically this says VOP of t, you have to choose it like this, that's all. Okay. And we also know that the difference of VOP and VOM is my actual output. That's how we have encoded our information. So what is VOP of t then? It's basically, this is plus, this is going to be minus. If you make sure they are, basically if they are exact negatives of each other, we will not have any interference caused onto any other line, right? And this is how we usually choose also. And in practice, most of the times you don't have negative supplies, so we add some DC voltage to it. Okay, I'll call it some output common mode VOC. And the simplest way to realize such differential circuit is this. Say have a single-ended system which takes in a signal Vi and gives a signal V0. Now what I can do is I give half the signal here, I get half the output. I can have an identical copy, apply minus Vi by 2, I'll get minus V0 by 2. So this is the input, this is my output. Okay. And now let's see what happens to the power supply rejection. So both of them will be connected to some power supply like this. So if there is any variations in the supply, so that will come here. So let's say this is again some K1 times V and DD. We'll have the same factor here, right? Because both these circuits are identical, both are having the same power supply. Okay. So any variations in that power supply will cause equal variations in the two outputs. So again, when you take the difference, this is going to be only V0. See? If we take the difference, this is going to be V0. So what can you say about the power supply rejection ratio here? It will be infinity. So as long as these two blocks are identical, then even this factor K1 will be same, then there will be no issues with power supply variations. Okay. And because of all these reasons, in practice, all analog and mixed signal blocks on chip, they will be fully differential like this. Okay. The only place where you will find single-ended signals is, say, you want to interface to the outside world. Say I want to pick up signals from a sensor. Sensors usually give a single-ended output, so you will have a block that takes in a single-ended input, but then it will do something like this. So that rest of all the blocks in our signal chain will operate on these differential signals. And similarly, if you want to connect to some transducer or say some speaker, you'll have to finally convert it to a single-ended output. But otherwise, all the other operations are done in a fully differential manner. So the bottom line is this: if you have this differential signaling, we will be immune to common mode disturbances. That is, any variations in supply or ground will not cause any issues, and also to interference. That is, we will not pick up any interference, and we will also not cause interference to some other signal. Okay. And yeah, as I mentioned, this is one way in which you can get this kind of a differential operation, wherein you take two identical blocks, give positive input to one, negative input to one, and do it. Let me remove the supply thing, that's not relevant now. So this will work, but do you think there is some issues in doing this? You might be knowing this already. I mean, this is a good solution, but in practice we don't do this. That is, we don't implement the differential operation like this. I think we also discussed in the beginning, and you should also be knowing it. So why don't we do this? Okay, so let's say this is now an amplifier. Okay, the gain A. What will be the output here? A times Vi by 2. This will be minus A times Vi by 2. So have a differential signal is getting amplified by a factor A. Looks all fine. But let's say I have some signal that is getting added to this. So what will be the contribution due to this signal now? At the output? Same thing, A times VIC. Here also plus A times VIC. Okay. Now again, if I take the difference, it seems fine. But the issue is this, right? I mean, this is some interfering signal that is getting added, right? And let us say the signal Vi, that is the actual signal you are interested in. Oops, sorry. Let us say this signal Vi is really small. Okay. But this signal VIC, that is the interfering signal, is relatively large. So what will happen is, because of this interfering signal, the output of the amplifier can easily saturate, isn't it? Although my actual signal could be really, really small, because of the fact that I have this interfering signal, because the interfering signal is also getting amplified by the same factor, I seem to be saturating my amplifier and I can't use it. Okay. So this implementation works properly for differential signals, but what is missing here? If you have a differential signal, what is the other thing? Common. This is basically a common mode, right? It's a common signal for both. It is also amplifying the common signal, isn't it? But that's not what we want. So you might be knowing common mode rejection ratio. You're familiar, right? This is essentially that, right? So what can you say about CMRR for this? Is it good or bad? This actually just a poor CMRR. Okay, and that is why I mean this kind of implementation is called pseudo-differential implementation. So you can use it as long as you are guaranteed that there is going to be no significant common mode variations. Okay, but in practice, what we'll implement is fully differential circuits. So which not only guarantee the right differential mode operation, but also have a good CMRR. Okay, is that fine? And the simplest fully differential amplifier is our diff amp. So let's say this is some I naught, and for simplicity I'll start with a resistive load like this. Okay. So I'll give my two inputs here, and the output is taken like this, right? So as you know, if I have any two signals, how can I decompose them? As a common mode plus a differential, right? So this is going to be the common mode plus a differential signal like this. Here it is common mode minus a differential signal. Okay. So now the circuit is properly symmetric, because essentially it looks like we have put two copies like this. So we have a completely symmetric circuit, so we can use half circuit concepts here nicely. So to find the output due to any combination of inputs, I'll first find the response due to differential signal, find the response due to common mode signal, and then I can add, right? I'm sure you would have done this, but let's quickly do it and finish today's class. So let us say now I am considering a differential signal where V1 is some VID by 2 and V2 is minus VID by 2. Okay, where VID is basically V1 minus V2. So this is VID by 2. Now if this is the case, what can you say about, I mean, can you do something to the circuit to simplify? We have already seen, right, all the nodes along this line of symmetry, what will be the potential, response signal potential? It will be 0, okay? And by the way, do you think this is valid for any circuit, or is there something that needs to be satisfied here? What needs to be satisfied? Sorry? No, there is nothing to do with the node impedance, right? Here we are looking only at symmetry. Why linearity? Okay, I think we also discussed in the beginning, please check that back. As he pointed out, linearity needs to be satisfied, and because essentially now we seem to be having two networks, and there is something connected here, right? The idea is here I am applying some plus V and minus V. If the network is linear, I can use superposition. So I can use superposition, find the response only due to plus V. Due to plus V, I'll have some, let's say, I don't know, some K1 times V here. Now I need to find the response due to minus V. The response due to minus V will also be same, right? Because the circuit is essentially the same, and that's why it is 0. So as long as the circuit is linear, all the nodes along the line of symmetry will be 0 if your excitation is fully differential like this. And of course, for small signals, our circuits are linear, so it's we can use it. So the circuit essentially reduces to this: source is ground, VID by 2, and of course, you know what is the output. What is the output here? Let's say minus GMR times VID by 2. Okay, and this is going to be, let us say, my VOM and VOP. So this is going to be my minus output, and VOM, I know it's minus V0 by 2. So you know minus V0 by 2 is minus GMR times. So VO by VID is GM times R. Okay, so let me quickly do common mode and end today. Now if I have common mode signals, that is both of them are VI and VI, how will the circuit simplify?
R by 2.
Yeah, again the idea is the circuit is completely symmetrical, inputs are same,
You can short the output.
so all these two nodes will be at the same potential, can go ahead and short them. So I have two resistors in parallel, so it becomes R by 2. I have two MOS transistors in parallel,
2W by
so if the dimension becomes 2W1 by L, and I have the current source. This is Vi. What is my output? 0. Incremental output is 0, right? Because I'm biasing it a constant current. What is the actual output? Total V out. I mean, incrementally it is 0, but what is the total output here?
I know. VDD minus
I not.
R by 2.
Right? So output is fixed to this value. Even if you change input, it's not going to change. So what is the common mode gain?
0.
So CMRR is. That's it. Okay. Let me write it and end. Okay. So let's stop here and we'll continue.